Welcome to EPG Pathshala. This module deals with different types of analog to digital converters. Continuously valued signal such as temperature, pressure, light intensity, which can take infinite possible values in between, is referred to as analog signal, whereas discretely valued signal such as integers encoded in binary is a digital signal. In the digital world, the processing, transmission of digital data is very easy and secure. Most complicated applications or a logic can be easily programmable in the digital computer compared to analog circuits. Here, an analog data is needed to be converted into digital one. There are number of examples where AD and DA converters are used. We are using a digital voltmeter to measure analog voltage and display the voltage in digital form. Here, the fundamental block of voltmeter is an AD converter. Another example is a digital communication system where we basically transmit an analog signal. At the transmitting end, we require analog to digital converter, whereas at the receiving end, we require digital to analog converter. An ambient temperature of an oven is monitored and controlled by a digital system. When temperature of an oven exceeds certain limit, it should make the heater off. Here, an AD converter is required to convert the output of a temperature sensor into digital form. If temperature exceeds the set limit, some digital output is generated which is to be converted to analog form in order to control the heater. There are different methods developed to convert analog signal to digital form. In this module, the flash and counter type ADC methods are studied along with its merits and demerits. Learning objectives of this module are to study parallel comparator or flash analog to digital converter, to understand its merits and demerits. Further, we are going to study the working of counter type analog to digital converters and its merits and demerits. The outline of this module is, after introduction, we are going to study the circuit diagram of simultaneous or flash AD converters. After that, we are going to study the merits and demerits of flash ADC. There are certain drawbacks of flash ADC and hence another methods are developed. The method that we are going to study in this module are counter type AD converter. There are further some merits and demerits of this counter type ADC and hence further methods are developed that we are going to study in the next module. Finally, at the end we are going to summarize the flash and counter type analog to digital converter. As we know, most of the quantities in nature like temperature, pressure, force, vibrations, light intensity are in analog form. The output of many sensors are also in analog form. It is found that the processing, transmission of digital data is easy as well as secure, and hence analog data is needed to be converted into digital form. Such an analog to digital converter converts an analog signal to an equivalent digital signal. AD converters are known as ADC or A/D or sometimes A to D converters. AD converters basically provides a link between analog world of sensors or transducer and the digital world of signal processing and data handling. There are various examples where we need such a analog to digital converters. As we know, the microphone accepts voice varying pressure waves in the air and convert them into varying electrical signals. We may have to convert such an output of a microphone into digital form. we know that strain gauges are used to determine the amount of strain when a stress is applied. We can convert such an output of a strain gauge into digital form using analog to digital converters. Another example where we require an AD converter is use of thermocouple for temperature measurement. As we know, the output of thermocouple is an analog one. If we want to convert the output of a thermocouple into digital form through some signal processing and using AD converter, we can convert output of a thermocouple into digital form. An ideal AD converters take an input voltage which is in analog form and convert it into a perfectly linear digital representation of analog signal. Such a digital representation is usually in the form of 0 and 1. AD converters, depending upon the output, may be a 4-bit, 8-bit, 12-bit and so on. If AD converter has got 8-bit output, then it is known as 8-bit ADC. If AD converter has 12-bit output, then it is known as 12-bit ADC. If we are using 8-bit converter, the binary representation of 8-bit will have 2 raised to 8 or 256 different values. If we are using an analog voltage in the range 0 to 5 volt to convert into a digital form, then 0 volts corresponds to 8-bit binary data, that is 0000 0000, whereas the 5 volt will corresponds to logic 1111 1111. In order to convert analog signal into equivalent digital form, several aspects comes into existence. For example, the analog signal may be a weak signal, analog signal may be a fast changing signal, and that is why the block diagram for AD system is shown here. The inputs may be from the sensor, is first given to the pre-processing block, which is then given to the anti-aliasing filter, which is basically restrict the bandwidth of the signal approximately or completely to satisfy the sampling theorem over the band of interest. After that, the signal may be sampled and finally given to analog to digital converter, which basically feeds the signal to digital processor. If the signal is fast changing, we require a steady signal at the input of analog to digital converter. This is obtained by a circuit known as sample and hold circuit. A sample and hold circuit is an analog device that samples the voltage of continuously varying analog signal and holds its value at a constant level for a specified minimum period of a time. If the input of ADC changing fast or to measure an AC voltage at a particular instant of time, a circuit as shown in figure can be used, which is known as sample and hold circuit. The first block is a buffer and the second block is basically a switch in shunt with an capacitor, which is used as a sample and hold circuit. The output of sample and hold circuit is then given to analog to digital converter. There are different methods to convert analog signal into equivalent digital form. The first method is flash type ADC, the counter type ADC, delta sigma ADC, successive approximate type ADC, single slope ADC and the dual slope ADC. In this module, the first method, which is the simplest method, probably the fastest method is the flash method, is studied. This flash type of ADC is also known as simultaneous method of AD conversion. It is based on number of comparator circuits, and hence the method is also known as parallel comparator type ADC. In parallel comparator type ADC, the signal which is to be digitized serve as a one input to the comparator, and the second is the standard reference voltage to the comparator. As shown in figure, a operational amplifier can be used as a comparator, where one input to the comparator is the analog input and another input is the reference voltage. Parallel comparator type ADC uses number of comparators. If we want a 2-bit digital output, for a 2-bit digital output, the parallel comparator type ADC requires 3 comparators. Figure shows the circuit of such a parallel comparator type ADC using 3 comparators. The analog voltage that we want to convert into digital form is applied to the one input of the comparator, whereas the other input to the comparator are the fixed reference voltage that may be obtained using potential divider arrangement as shown in figure. The reference voltage to lower comparator is V by 4, the reference voltage to middle comparator is 2V by 4, whereas the reference voltage to upper comparator is 3V by 4. Depending upon the analog input voltage, the comparator outputs that are C1, C2 and C3 are set. When the input analog voltage is within the range of 0 to plus V by 4, it is found that the output of the comparator C1, C2 and C3 will be low or at logic 0. When input analog voltage increases, and if it is in the range of plus V by 4 to plus V by 2, it is found that the output of lower comparator gets set, and that is why C1 output becomes high, whereas for the comparator C2 as well as C3, still the reference voltage is more than the analog input voltage, and that is why the output of C2 and C3 will be low. When input analog voltage is further increased and it is in the range of plus V by 2 to plus 3V by 4, it is found that the output of C1 and C2 will be high, whereas the output of C3 will be low. When the analog input voltage is further increased and if it is in the range of plus 3V by 4 to plus V, for all the 3 comparators, the analog input voltage will be more than the reference voltage, and that is why the output of comparators C1, C2 and C3 will be high. Thus, for the figure shown, the reference voltages are plus V by 4, plus V by 2 and plus 3V by 4, and if this is the case, then this system can be used to convert an analog voltage in the range of 0 to plus V in order to convert into digital form. This output of a comparators can be coded using a network to obtain the digital output. For the coding purpose, we can use logic gates, and it is obvious that using 4 different possible combinations of output of a comparator, we can have 2 digital outputs, D0 as well as D1. Figure shows the coding network using logic gate. Input to the coding networks are the comparator outputs C1, C2 and C3, whereas the coding network will have outputs obviously digital one, D0 bit and D1 bit. For this circuit, when C1, C2, C3 all are low, the circuit will generate the output D0 bit and D1 bit 0, 0. Whereas when the analog voltage is within the range of plus V by 4 to 3V by 4, in that case C1 output will be high, C2 and C3 will be still low, and this coding network will generate the digital output 0 and 1. When C1 and C2 are high and C3 is low, digital bits generated will be D0 bit 1 and D1 bit 0. Whereas when C1, C2 and C3 all 3 bits are high, the digital output generated will be 1, 1. Thus, the coding network accepts the output of comparators and convert the comparator outputs into 2-bit digital form. Figure shows the circuit diagram of 3-bit parallel comparator type ADC, which basically uses priority encoder. Means rather than using discrete logic gates as a coding network, here we can use priority encoder. As we know, for a priority encoder, the circuit generates the output corresponding to highest numbered input, and hence depending upon the analog input voltage, the comparator outputs will be set, and these comparator outputs will activate the inputs of priority encoder, which will generate the digital output. We are using here a circuit diagram for 3-bit comparator, and hence for a generation of 3-bit analog to digital converter, we require 7 comparators. One input to these comparators are again the analog input voltage, whereas the other input is the fixed reference voltage obtained using potential divider arrangement. When the analog input voltage is less than the reference voltage of lower comparator, output of all the comparators C1 to C7 will be low. Suppose we assume that the logic 1 equal to 8 volt, then plus V connected to the circuit is suppose 8 volt, then when V in is less than 1 volt, output of all comparators C1 to C7 will be low or logic 0. Whereas when analog input voltage is increased, and if it is in the range of suppose 1 volt to 2 volt, then only output of C1 will be high, all other comparator outputs will be low. Whereas when output will be in the range of 2 volt to 3 volt, output of comparators C1 and C2 will be high, whereas all other comparators will be low. In this way, if we increase the voltage up to 8 volt, and if it is within the range of 7 volt to 8 volt, it is found that output of all comparators becomes high. These outputs can be used to activate the priority encoders, and which will generate the digital equivalent of this analog equivalent input. Let us review the parallel comparator type ADC method. This method, as the name suggests, uses number of comparators. One input to the comparator is the reference voltage, which is obtained using potential divider arrangement, whereas the other input is the analog voltage, which we want to convert into digital form. As the method uses number of comparators, it is known as parallel comparator type ADC. It is found that the conversion time of this ADC is very small. As soon as we apply the analog voltage, that is converted into equivalent digital form, and that is why the method is also known as flash ADC. Only drawback of this method is the number of comparators required. As we have seen, for a 2-bit ADC we require 3 comparators, for 4-bit ADC we require 15 comparators, for n-bit ADC we require 2 raised to n minus 1 comparators. Thus, even though the conversion time is small, the major drawback of this flash type ADC is the number of comparators required, and that is why this method is not used always. We have to see the other methods of conversion of analog signal into digital form. Flash ADC has got certain advantages and certain drawbacks. The first and the very important advantage is it is very fast. The second important advantage is the method is straightforward and very easy to understand. There are few drawbacks or disadvantage of flash ADC. It requires large number of parts in the form of comparators. For 8-bit ADC, we require 255 comparators. This method has got relatively lower resolution. As the total number of parts are more, the method becomes more expensive. Further, this method has got large power consumption. To overcome the drawback of parallel comparator type ADC, a counter type ADC method is developed. Basically, this method is used whenever we require higher resolution. As we know, in case of flash type ADC, we require a reference voltage to the comparator and the other input is the analog voltage that we want to convert into digital form. It is found that if a variable reference voltage is available, we can use a single comparator to convert analog voltage into digital form. And this technique is used in counter type ADC where only one comparator is used. As shown in figure, one input to comparator is analog input, whereas the other input, which is the reference voltage, which is not steady but a variable reference voltage. The reference voltage can be applied to the one input of the comparator and the other input will be the voltage that we want to convert into digital form. When the reference voltage becomes equal to the input analog voltage, the conversion will be complete. It is found that counter type ADC requires DAC as a part of it in order to convert or in order to obtain variable reference voltage, and hence the counter type ADC requires comparator, a clock and a control logic. Figure shows the block diagram of counter type ADC. As shown in figure, it contains a comparator, a clock, a gate and control circuit, counter, level amplifier, a binary ladder. The output of a binary ladder is a variable reference voltage given to the input of a comparator. The width of the counter, the width of the level amplifier or binary ladder depends upon how many bit ADC we require. If we require 8-bit ADC, we require 8-bit counter. The output of a counter are fed to the level amplifier, which adjusts the digital level to the proper value. Further, the output of a level amplifier is given to binary ladder, which will convert digital input into equivalent analog voltage, and this analog voltage serve as a input to the comparator. To begin with, the counter is reset so that counter output becomes 0 0, which makes output of level amplifier also all zeros. Input to binary ladder will be 0, reference voltage to the comparator will be 0. If analog input applied is positive, output of the comparator will be positive. The gate and control circuit will open and the clock is applied to the counter. When the clock pulses are applied to the counter, the content of counter progresses from 0 0 0 0 0 0 0 to 0 0 0 0 0 0 0 1. After proper level adjustment, this digital data is converted into analog 1 using binary ladder, which will function as an input to the comparator. This reference voltage and the analog input will be compared by the comparator, and the comparator output will be either low or high depending upon whether the analog input is greater than or less than the reference voltage. When the reference voltage is smaller than the analog input, output of comparator will be still high. The control circuit will pass the clock pulses to the counter and the content of counter advances. In this way, as long as the analog input voltage is less than the reference voltage, the clock pulses are applied to the counter will advance and the binary ladder will convert that digital data into analog 1, which will acts as a input to the comparator. Thus, the counter starts counting these clock pulses and its output goes on increasing. As the counter outputs as an input to DAC, the DAC output also increases. As long as DAC output is less than VA, the process will continue. The comparator output remains high, enabling the AND gate. As soon as DAC output is higher than the input analog voltage, the comparator output becomes low. This will disable the AND gate and stop the clock pulses. Thus, the counting stops and the digital output of the counter then represents the analog input voltage VA. In counter type ADC, the counter advances one count for each cycle of the clock. The clock therefore determines what is known as the conversion rate of ADC. As we know, the conversion rate is the time taken by the circuit to convert analog voltage into digital form. If we are using a 10-bit converter, it will require 1024 clock pulses for full scale output. So, if the clock frequency is 1 megahertz, then counter will advance after every 1 microsecond. For a full scale output of 10-bit ADC, then will require 1.024 millisecond. This is the situation when counter has to advance to its maximum value, but the average conversion time for a 10-bit converter will be half of this, and that will be then 0.512 millisecond. Let us consider the merits and demerits of this counter type ADC. Counter type ADC is a very good method for digitizing a signal to a higher resolution. It is found that this method is much simpler than the simultaneous method for higher resolution of conversion. However, this method also has got certain drawback. The drawback of this counter type ADC is its conversion time. It requires as many as 2 raised to n counts before conversion is complete. In fact, the average conversion time will be 2 raised to n minus 1 for the conversion to complete, where n will be the number of clock pulses. These clock pulses are fed from the clock, and hence the clock frequency is going to decide the conversion time of counter type ADC. Let us summarize this module. We have seen two methods of conversion of analog signal to digital form. The first one is flash or simultaneous AD converter, which is basically built using number of comparators. It is found that this method is very fast, conversion time is small, and that is the strongest advantage of parallel comparator type ADC. However, for n-bit flash AD converter, we require 2 raised to n minus 1 comparators, which increases cost and the power consumption of parallel comparator type ADC. This method hence is not suitable for converting analog signal to a digital form with higher resolution, and hence a counter type method of ADC is developed which uses variable reference voltage as a one input to the comparator and analog voltage which we want to convert to digital form as a other input. This is a straightforward method of converting analog signal into digital form, which is basically used whenever we require higher resolution, but the drawback of this is conversion time, and hence a compromise has to be used whether to use a parallel comparator type method or a counter type method will be decided by the application. When we require a small conversion time, a parallel comparator type method is developed and used, whereas when we require higher resolution, a counter type ADC is used.